Hi, this is Wei. In this talk, I'll introduce Neural Predictor for neural architecture search. This is a joint work between Google Brain and Duke University. Neural architecture search, or NAS in short, often uses complex algorithms to find the best architecture. We propose an approach that's much simpler. First, we randomly sample a small set of N models and train and validate them. So we can get a dataset of pairs of architectures and validation accuracies. Then we use this dataset to train a regression model that predicts validation accuracies for architectures. Next, we use this regression model to predict the validation accuracies of a large number of random architectures. Finally, we train the top K predicted models and deploy the model with the best validation accuracy. In this paper, we use graph convolutional networks as the regression model to predict accuracy. Details are in the paper. Before we dive into our method, let's talk about the recent state of NAS. Popular NAS method required to run the whole search process again and again to tune the hyperparameters. Basically, they set one set of hyperparameters, run the NAS, and find the model. Then they try a new set of hyperparameters and find another model. They keep doing this until a good model is found. Therefore, the total search time should be a single search time multiplied by the number of repeats when tuning hyperparameters. The table includes the major hyperparameters for different NAS methods. Unfortunately, when comparing the efficiency of NAS methods, they only compare a single search time under the best tuned hyperparameters. One major advantage of Neural Predictor is that it's very friendly to hyperparameter tuning. Basically, after we train n random models to obtain the dataset, the hyperparameters that we have to tune is the architecture of the regression model and its training hyperparameters. This is a standard cross-validation in the supervised learning, which can be done using this single dataset we obtained. Therefore, we don't need to rerun any steps ahead. Tuning those hyperparameters is fast because the regression model is very small. After we build the predictor, we run a single search to find the best model. The only hyperparameter that we might need to rerun the whole process is n, which is the number of models used to build a neural predictor. We'll discuss it later. Another big advantage of our approach is its full parallelizability. For NAS based on reinforcement learning, evolution algorithm, or Bayesian optimization, the compute can be parallelized within each step, but synchronization is demanded to collect signals such as reward in reinforcement learning, fitness in the evolution algorithm, and acquisition in Bayesian optimization. Weight sharing is more efficient, but it trains a gigantic model sequentially using an iterative optimizer. However, in Neural Predictor, the most computationally intensive components of the method are fully parallelizable. Those components are training n random models and training top K predictive models. In summary, comparing with previous work, our method is hyperparameter friendly and fully parallelizable, and we'll show soon that Neural Predictor is also efficient. Result on NASBench 101. To evaluate our method, we adopted some reasonable baselines. The first one we call Oracle baseline, which is the upper bound that any method cannot exceed. In this baseline, we train all models in the search space and pick the best validation model. The left figure is validation versus the number of trained samples or models. The middle figure is the test accuracy, and the right figure is the test accuracy versus walk clock time. The second baseline is random search, which is a lower bound that any next method should compare with. In this baseline, we train some random models and pick the best validation model. The last baseline is regularized evolution, the best method in the original NestBench 101 paper. Our results show that Neural Predictor is more than 20 times as sample efficient as regularized evolution and approach the upper bound for test accuracy after about 350 samples. In this example, we use n equal to 172 models to build the predictor. This is the vertical line in the figure where we start to train top K predicted models. In the use of Neural Predictor, we may want to ask this question. Given the total number of models that we can train, what's our optimal n? The figure shows the result. Obviously, if n is too small, the predictor is not accurate and the Neural Predictor can be less efficient. However, if n is too large, a small top K models are left to evaluate under the limited budget. In this way, it cannot tolerate the prediction noise in the predictor and can also underperform. However, in the figure, Neural Predictor with all n values can still outperform regularized evolution. Our method is efficient to scale to ImageNet. We use the same search space of proxiness, which is the near state-of-art baseline to produce efficient models for mobile devices. The result of Neural Predictor below was produced by our first single run. We simply set n equal to 120 based on our compute budget we had. However, for proxiness, we had to tune its hyperparameters by running multiple times to reproduce a good result. In the left figure, we predicted the accuracies of about 1 million random models with the inference time between 75 and 85 milliseconds. Then we trained the models on the predicted frontier in green, which includes 137 models. Based on the trained frontier, we can obtain the true frontier in the middle. The right figure includes simply the true test accuracies. As we can see, our method is on par with the proxiness while being more friendly to hyperparameter tuning and fully parallelizable. Moreover, a single run of Neural Predictor can produce the whole trade-off curve, but the heavily tuned proxiness can only produce a single dot. Conclusion and takeaways. Neural Predictor is simple, sample efficient, friendly to hyperparameter tuning, and fully parallelizable. Using graph convolution networks as the predictor is more effective. For the purpose of reproducibility and fair comparison of nest methods, we followed, and the community should follow, the following rules. First, search by validation accuracy and use test accuracy for final report only. Second, use the same search space for comparison. And finally, comparing the search time of a single run is not sufficient. The cost of tuning hyperparameters should be discussed. Thank you.